Hi everyone, welcome back to Coding Fab. In today's video, we're going to build a project called Medical Cost Prediction using Python and machine learning. You'll learn how to load and explore real-world data, clean and prepare it, choose important features, train a linear regression model, and evaluate how well it performs. This is a great beginner-friendly project to practice data analysis and modeling step by step. All right, let's get started. 1. Understanding the project. This project is a regression-based machine learning task focused on predicting individual medical charges using personal and lifestyle attributes such as age, BMI, number of children, gender, smoking status, and region. The dataset sourced from Kaggle is in tabular format and well-suited for applying supervised learning techniques. The goal is to develop a model that can estimate medical costs based on these features, providing insights into which factors contribute most to variations in healthcare expenses. Linear regression is chosen for its simplicity and interpretability, and categorical variables were handled using one-hot encoding during preprocessing. The project was implemented in Jupyter Notebook, utilizing essential Python libraries such as pandas for data manipulation, scikit-learn for modeling and evaluation, and matplotlib and seaborn for data visualization. All right, let's dive in. 2. Data collection. Let's download the dataset into your system. In this example, we use the Kaggle Medical Cost Personal Dataset. Kaggle is a popular machine learning platform with datasets. You can find the dataset from the dataset page on their platform and download it as a CSV file. It looks like this. You'll see the features such as age, sex, BMI, children, smoker, and region, and the target label, which is charges. 3. Load the data. After downloading the data, open your preferred IDE, such as Jupyter Notebook, and create a new notebook. Also upload your dataset. You can paste it to the same folder. Then import pandas and load the CSV file by using pandas read CSV to load the dataset into a data frame. Data frame is often named as DF for short. Also make sure the file name matches exactly what you uploaded. In this case, insurance CSV. Now you can view the first few rows using head method to see what your data looks like, such as the target label, charges, and other features. 4. Explore the data. Before you build a model, you need to understand your data and make sure it's clean. Dirty or messy data leads to bad predictions. For example, info method shows a summary of the data frame structure, including the index range, number of columns, column names, non-null values per column, and data types. It says the total entries are 1338 rows and no missing values. Numerical columns are age, BMI, children, and charges. Categorical columns are sex, smoker, and region. Another method is describe. It shows a quick summary of your data set. For numeric columns, count mean, standard deviation min 25, 50, 75%, and max. For categorical columns, count, unique, top, and frequency. Let's quickly highlight the key insights. First, age ranges from 18 to 64. Median is 39. 676 are males. BMI ranges from about 16 to 53. Median is about 30.4. As for children, most people have 2 children. Max is 5. 1064 out of 1338 are non-smokers, very imbalanced. Most people are from the Southeast, 364 people. Charges have a huge range from 1,121 to 63,770. Very skewed. So we can get a lot of information in this step. These are the other useful exploration methods. Please try them out and explore the data further. The details of each method are explained in the other video. And also visualization is important in the exploring step. It helps detect patterns, spot outliers, understand correlations, and present insights more easily to others. These graphs are drawn using the format shown in the lower right. It imports Matplotlib and Seaborn first. Then create a canvas and set the size of the plot. After that, write a main plotting command, which can be replaced with histplot for distributions, scatterplot for relationships between two numerical variables, and a boxplot for comparing distributions across categories. You can pass the relevant data frame columns to those functions. Then set your chart's title and axis labels to clearly explain what the viewer is seeing. Finally, display the plot with the show method. All right, let's walk through each graph step by step. First, the distribution of medical charges shown in the upper left. The distribution is skewed, long tail on the right. Most patients are charged under $15,000, but a few have very high charges. Seems to have outliers. So we can consider transforming the target variable if needed for certain models. Next, medical charges by smoker status. This graph shows that smokers have significantly higher medical charges than non-smokers. The median charge for smokers is over $30,000, while it's below $10,000 for non-smokers. So this is a strong indicator that smoker is a powerful predictor. Next, sex versus charges. The box plot shows that there is no strong relationship between sex and their medical charges. Both males and females have similar distributions, with overlapping medians and comparable variability. Therefore, while sex can still be included as a feature for completeness, it does not appear to be a strong predictor of medical costs on its own. Next, charges versus BMI colored by smoker. Smokers with higher BMI tend to have very high charges. For non-smokers, charges remain lower even at higher BMI levels. BMI alone has a moderate effect, but in combination with smoker, the effect is strong. Next, charges versus age colored by smoker. Charges increase with age, especially for smokers. Smokers are consistently charged more across all age groups. So there is a strong relationship between age plus smoker and charges. Next, medical charges by region. There is no major difference across regions. Slightly higher charges in the Southeast region. So region may not be a strong predictor, but still useful for completeness. 5. Cleaning the data. Before moving forward with modeling, we'll do a data cleaning step to ensure the dataset is accurate, consistent, and free of issues that could negatively affect model performance. First, we check for missing values using the is-null sum method. Fortunately, there are no missing values in any of the columns, so no further action is needed in that regard. Next, we check for duplicate rows using duplicated sum. We see one duplicate record, which can remove using drop duplicates. Removing duplicates helps prevent bias or overfitting during training. Next, inconsistent data. Check the categorical data like sex, smoker, and region by examining their unique values, because sometimes there are typos, but seems like all values are consistent and clean, no typos, unexpected values, or formatting issues. So we didn't need to make any corrections here. Finally, look for outliers, particularly in the charges column using a box plot. While observing some high medical charges above $50,000, these are likely legitimate cases, like smokers with health issues. So for now, let's keep all data as is and ignore outliers. Here's the quick summary of this step. If you have missing values, you can follow these strategies. Here's a quick summary of options to handle missing values for numerical columns and categorical columns. For numerical columns, there are largely 7 ways. Mean imputation replaces missing values with the average of the column. It's simple but sensitive to outliers. Median imputation is better for skewed data because it's less affected by extreme values. Mode imputation fills missing numbers with the most frequent value, useful for discrete numerical values. Constant value lets you fill in a specific number like 0 or 1 to indicate missingness clearly. Interpolation estimates missing values by looking at neighboring data points. This is ideal for time series. Predictive modeling uses machine learning or regression to estimate missing values. This is accurate but complex. Drop rows removes records with missing values, best used when only a few rows are affected. For categorical columns, there are largely 5 options. Mode imputation is most common. It fills in the most frequently occurring category. Constant label lets you insert placeholders like unknown or missing to indicate data was not provided. Frequency encoding uses your domain knowledge to insert the most common or likely category. Predictive modeling predicts the category based on other features, more advanced but effective. Drop rows removes missing entries if they are rare or not critical to your analysis. Here are the tips for choosing a strategy. Use mean or median for numerical values, depending on the distribution. Median is for skewed data. Use mode or unknown for categorical data. Drop rows only if the number of missing values is small. For critical columns with many missing values, consider domain knowledge or predictive modeling. 6. Feature selection. In this step, you'll separate the dataset into 2 parts. Features, the input values the model will use to learn patterns, and target, the value you want the model to predict. This step matters because your model learns from features to predict the target. So choosing the right features is critical for accuracy. To select the most relevant features for predicting medical charges, we used a combination of domain knowledge, correlation analysis, and visualization. From a domain knowledge perspective, it's reasonable to assume that a person's age, BMI, number of children, and especially whether they smoke, would significantly impact their medical costs. Additionally, factors like gender and region may contribute to variation even if the impact is smaller. To support this, we check the correlation. Since correlation analysis only works with numeric data, first convert the categorical variables such as smoker, sex, and region into numeric form using the map method and encoding. This allowed us to compare them directly with the target variable charges in the correlation. Note that while smoker and sex are binary and can be directly mapped to 0 and 1, the region variable has more than 2 categories and no inherent order. Therefore, it requires one-hot encoding, which we will implement properly in the pre-processing section. Next, visualization. We visualize the data using scatter plots and box plots in the exploring data section like this. Those revealed that smokers consistently have much higher charges, and that older individuals and those with higher BMI also tend to incur greater costs. While the impact of region and sex is less clear, we will include them to allow the model to capture any subtle trends. Based on these insights, decided to select the following features for our model: age, sex, BMI, children, smoker, and region for features, and charges for the target value. 7. Pre-processing. The main goal of the pre-processing step is to prepare the raw data into a format that a machine learning model can understand and learn from effectively. This includes handling categorical variables, splitting the dataset for training and testing, and optionally scaling numerical features. Proper pre-processing ensures that the model trains accurately and generalizes well to new data. First, we apply one-hot encoding to convert categorical variables into a numeric format. This is necessary because machine learning models like linear regression can only work with numerical input. We use the pandas get dummies function with drop first true to avoid the dummy variable trap, which can cause multicollinearity. This approach replaces each categorical column with a set of binary 0 or 1 columns representing each category, excluding 1 as the reference. For example, the smoker column is transformed into a single binary column, smoker_yes, while region, which has 4 categories, is converted into 3 binary columns, like region northwest, region southeast, region southwest, with one region dropped as the baseline. More specifically, if we don't use drop first, region has 4 unique columns. Each of these columns indicates whether a row belongs to that specific region 1 or 0. However, this introduces a problem known as multicollinearity, when one feature can be perfectly predicted from the others. This redundancy can confuse the linear regression model, leading to unstable or inflated coefficient estimates. That's why we have to drop one category like this. Now, the dropped category becomes the baseline or reference group. The model will compare the effect of other regions relative to this baseline. After pre-processing the features, we split the data into 2 parts, a training set and a testing set. The training set is used to teach the model, while the testing set is used to evaluate how well the model performs on new, unseen data. We typically use an 80 and 20 split, where 80% of the data is used for training and 20% is used for testing. This approach helps prevent overfitting and provides a realistic way to measure model accuracy. We use train-test split from scikit-learn to do this efficiently, ensuring the model is trained on a representative sample and evaluated fairly. We don't not apply feature scaling here, as it is not required for basic linear regression, when all features are already on a similar scale or are one-hot encoded. Next, train the model. The goal to use the training data to teach the model how to make predictions. During training, the model looks at the input features and tries to learn how they relate to the target values. Linear regression finds the best fit line by minimizing the difference between predicted and actual values. This is called minimizing the error or loss. Let's use linear regression from scikit-learn. First, import the model and create the model. Then train the model using the fit method. Now the model has learned the relationship between the features and the target. After training, you can check feature coefficients and intercept. They are used to check the learned equation. Coefficients give you a list of weights or slopes for each feature. These values tell you how much the predicted medical charges change when that feature increases by 1 unit, assuming all other features stay the same. Intercept is the value of charges when all feature values are 0. It represents the baseline medical cost before adding any influence from the input features. For example, this is the result of coefficients. It shows high positive coefficient, so being a smoker significantly increases predicted medical charges compared to a non-smoker. On the other hand, region Southeast has a negative coefficient, so people in the Southeast region are expected to have lower charges than those in the base region. The intercept might be large, but doesn't always have practical meaning unless all features can realistically be 0. 9. Prediction. After training and evaluating the model, the next step is to make predictions on unseen data and compare them with actual values to assess how well the model performs in real-world scenarios. Let's start by generating predictions for the test set using model predict method. It uses the trained linear regression model to predict medical charges for each observation in the test data set. Next, create a comparison data frame to visualize and compare actual versus predicted values. This creates a side-by-side table of the true charges and the model's predictions for each patient in the test set. To evaluate these predictions visually, let's create a scatter plot using Seaborn. Each point in the plot represents one patient. If the prediction is perfect, the point will lie exactly on the diagonal line. This part is to add a reference line. This line represents perfect predictions. Points that are close to this line indicate accurate predictions, while points far away suggest prediction errors. Let's look at the graph. The model does a reasonably good job of predicting medical charges overall. In the lower charge range, most points are close to the red line, meaning the model is performing well. However, it underestimates charges for high-cost individuals, which may be due to the nonlinear effects of some features in certain ranges. While the model captures the general relationship well, a more flexible model, like decision trees or ensemble methods, might improve prediction in the high-cost cases. 10. Evaluation. Let's evaluate how well the model performs. Let's start by generating predictions for both the training set and the test set by using the predict method. Next, calculates the MSE, RMSE, and R2 score for both training and test sets like this. Mean squared error measures the average of the squared differences between actual and predicted values. Lower values indicate better performance. Root mean squared error is the square root of MSE. This is easier to interpret than MSE. R2 measures the proportion of variance in the target variable that is explained by the features. It ranges from 0 to 1. A score closer to 1 means better fit. Now let's look at the results. First, it shows a good predictive performance. The model has an R2 of 0.78 on the test set, which means it explains about 78% of the variance in medical charges, a strong result for real-world data. Also, this indicates that the model is doing a good job of capturing the main patterns and relationships in the data. Second, no overfitting. The test RMSE is slightly lower than the train RMSE. It suggests that your model is not overfitting and may even be generalizing a bit better on the test set. Third, the error magnitude. An RMSE of around 5,800 means the model's predictions are on average off by about 5,800. Given the wide range of charges from around 1,000 to 60,000 plus, this is a reasonable error and expected in health cost prediction. If you want to improve performance further, consider using nonlinear models like random forest or XGBoost, or applying a log transformation on charges to reduce skew. And that's it for today's lesson on this topic. We started by understanding the goal of predicting medical charges using real-world data. Along the way, we explored the data set, cleaned and prepared the data, selected important features, and built a linear regression model. We wrapped it up by evaluating the model's performance and discussing how the results can be interpreted in a practical setting. Hopefully, you now have a clearer idea of how to approach similar machine learning problems on your own. Okay. Thanks for watching today's lesson on coding Fab. I hope you found these tips useful and feel more confident. Remember, practice makes perfect, so try using these tips in your project. If you enjoyed this video, don't forget to give it a thumbs up, share it with your friends, and subscribe for more Fab coding lessons. Until next time, keep practicing and stay Fab.